Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In this video, we want to look at how we could write our traversals or some of the other functions that we might want for trees on the kind of simple beginning of a general tree that we started writing a few videos ago. So we started off saying that we could implement our general tree. This is a tree that has an arbitrary number of children per node by creating nodes that store whatever data it is, and for our example, we're not really going to care about the data yet. We'll have an example shortly where we start to worry about that more. And then we need a sequence of children, so however many children the node might happen to have. So if we had this type of setup, how would we do our different traversals? So for example, let's say I wanted to write a preorder traversal. Well, if I write a preorder traversal, when we're talking about this, I talk about the fact that you visit the nodes. And remember, a preorder traversal, you visit the node before you visit any of its children. What does it mean to visit? Well, in some ways, you don't know. And so when you're writing code for this is a great place to pass in a function. So I want to pass in a function called visit. And this function takes in an A and returns unit. We don't really care what it is. It's just some function that we can call because we're not going to use the return value from it. The outside code is going to set up whatever function this is. We're just going to call it for every one of the nodes in the tree. We're going to do this recursively using a depth first search in the preorder. So preorder, we visit here before we go to our children. Now I need a recursive function, and we could add a recursive argument here, but what I'm actually going to do is I'm going to nest inside of here a little function called recur, and it's going to use the visit function, but it needs to be passed a node in there. And so this is where the actual work is going to be done. And the function for preorder is simply going to call recur on the root. Okay. So what do we do inside of recur? Well, oops, we don't have a root. Let's add that real fast. Private. I can say val right now. We don't really care too much. If this were a real implementation, we'd probably have to make it a var because it would change over time, but that's not significant to us right here. We're instead caring about this traversal. So because this is a preorder, we're supposed to visit this node, visit of in's data, and after we visited the node, we should go and recursively descend to all the children. So I'm going to write for C in children, recur on C, in.children. Okay. So we visit the data for this node, and after we have visited the data for this node, we run through all of the node's children in order and do the recursion on them. And so what this is going to do when we call this first on the root here is it does the visit on A, and then it will call in order visit on, or it'll call the recur on B, on C, and on D. But of course, the way the recursion works, it's not going to go to C until it is completely finished with B. So B is going to wind up, the call to B is going to wind up going down to E, and then that will pop back up, and then we'll remember and we'll come over to C, and it will finish doing all of these, and after C is done, then we'll come over to D. So while it might be tempting to think that this is going to go B, C, D in order because we run through the children, remember this recur is another call to the same function. It's an interesting question here. Recursive functions should have a base case. What is the base case for this? And it turns out the answer is if children is empty. So in the case where the sequence of children is empty, this for loop never happens, and so the recursive function never gets called. So that's a preorder traversal. What about a postorder traversal? change the name to Postorder. The change is remarkably simple. That's it. Okay. That's what a Postorder traversal looks like. It goes to the children first, and then it visits the data after it's done. Okay, we talked about some values that we could define for a node. So why don't we go ahead and write maybe two of these. So for example, we talked about the height of a node in the tree. So I might ask what the height of a particular node is. Well, we said that the height of a node is given by how many edges it is down to the lowest leaf. So this entire tree has a height of 3. So the height of a leaf is 0, and the height of everything else basically grows up from that, and you take the maximum. So in the case of here, the B has a height of 1, D has a height of 0, but C has a height of 2, and that's what determines the height of A. Okay, so this is going to be a recursive function. I want to go through all of the children and combine them using a max. And then, but I have the situation where what happens, well, there are two possibilities here. I guess actually we won't ever go to it. So if there are no children, actually, will this work? Let's try this. Do this where the base case is kind of implicit, just like we had before. So I'm not going to write an if. How about we do this? Let's do children dot fold left, starting with 0, and the function that I'm going to write here takes the H so far and a child node, and is supposed to return well, I'm just going to take, what I want to do here is take the maximum of these. So I'm going to change that to be a -1 of H max the height of C. And that should be in dot children again. I seem to like doing that. What are we unhappy with here? Oh, H is an int and C is a node. That mismatch. Oh, because height is supposed to return an int. Equals. Okay, let's properly finish the signature there. So what this is going to do is it's going to find the maximum height of all of the children, and note that it gives you a -1 as the base case. So if there are no children, this should give us back a -1. So I'm going to add 1 to it. You could write this in lots of different ways. I think the fold left just is a good example of using a higher order method to do it. What about the case of our size? Well, size is actually even potentially a bit easier. N is a node, so I want to find the size of the node. Once again, this is the function returns an int. So I need to run through all of the children of that node. How do we find the size of a particular node? Well, so let's say if I want the size of C, that would be, it's the size of everything in this subtree. So that happens to be the size of F, which is 2, plus the size of G, plus 1. So that's exactly what I want to do. I want to recursively call size on all of the children and then add 1 to that result. So I'm actually going to run through all of the children, and we can do this again with a fold left. I'm going to start at 0 here because this is a summation, and I have my size and my child. I want S plus the size of the child, and can have the +1. Actually, I think I'm going to put the +1 back at the beginning like I did on the previous function. And there we go. there is a size function. We'll hit these again for binary trees because these can look a little bit different depending upon the tree, but hopefully this shows you how we can define these types of functions recursively. And we'll come back in our next video and we'll go through an example that I like to, we'll go through an example that I like to do of parsing formulas, and then we'll look at binary search trees, which is a specific type of tree.